Good morning. In today's lecture, I'm going to continue my discussion on deadlocks. In the last class, we were discussing about Banker's algorithm, which is used for deadlock avoidance. If operating system does not employ deadlock prevention or deadlock avoidance mechanism, then the operating system has to allow deadlock to occur and use an algorithm to detect and another mechanism to recover from it. We in the last class discussed about one of the approaches for deadlock detection, that is wait for graph approach. Wait for graph is a data structure. It has processes as nodes and edges connecting them. If there is an edge from process A to process B, it means that the process A is waiting for a resource which is held by process B. If you observe a cycle in such a wait for graph after it is being constructed, then we say that there is a deadlock in the system. But there we made an assumption that the system has single instance of each resource type. So wait for graph cannot be used when the system has multiple instances of each resource type. So in today's lecture, I'm going to discuss about an algorithm that could be used to detect the deadlock when the system has multiple instances of each resource type. Okay, before I discuss about the algorithm, we have to know what are the data structures that are used by this algorithm. Like Banker's algorithm, here also we make use of data structures like available and allocation. Available is a vector of length m which indicates the number of available resources of each type. Allocation is an n cross m matrix which defines the number of resources of each type currently allocated to each process. And there is one more data structure, that is a request. This is also an n cross m matrix, indicates the current request of each process. That is, if request of I comma j is equal to k, then it means process pi is requesting k more instances of resource type rj. Okay, these are the three data structures that are used by this algorithm for detecting the deadlock. Let's go to the next slide and see how this algorithm works. So this algorithm is looking similar to the safety algorithm which was used in Banker's algorithm. Here also we use work and finish data structures. Both are vectors of length m and n respectively, where m indicates number of resource types and n indicates number of processes. So initially in step 1 we equate available, which is a vector, to work, which is also a vector of length m, and then we make this finish of I, which is also a vector, to false if allocation of I is not equal to 0. What is the meaning? Now you will have to think and tell me that if allocation is equal to 0, it means that that process will not participate in the deadlock because it is not holding any of the resources. So therefore what we do, if the allocation is not equal to 0, only then we make a finish of such a process is equal to false. Otherwise finish of I is kept as true because it will not have any impact on the deadlock. In the second step, like what we did in the safety algorithm of the Banker's algorithm, in the second step we find an I such that both finish of I should be equal to false and request of I should be equal to or less than work. If we don't find such an I after the complete loop is executed, Then we go to step 4 and see there whether any of the finish of I is equal to true. That I have put here. Let me erase this. Okay, we go to the step 4. Here we check if finish of I is equal to false for some I that varies from 0 to n. Then the system, if that is true, then the system is in deadlock. Or if finish of I, where I varying from 0 to n, if all those elements are equal to true, that means the system is not there in the deadlock state. Okay, and you can also determine what are the processes that are contributing to deadlock. If finish of I is equal to false, you can say that Pi is deadlocked. The process Pi is deadlocked. Okay. Now let's go back to the algorithm again, which we were discussing. And if we find an I such that finish of I is equal to false and request of I is less than or equal to work, what is the meaning? That its request can be granted. So whatever resource that we have allocated to this process, we claim that back, or we add that to the work. We simply add that to the work and make finish of I is equal to true. And then go back to the second step again and see if there is any other process whose request is less than or equal to work. If yes, then again do this. That is, you add its allocation to the work and make its finish is equal to true. This process is repeated until we visit all the processes. Once that is done, we come to this fourth step, and here we see whether all the elements of finish is equal to true. If it is equal to true, then there is no deadlock. If there is some finish of I which is equal to false, that means the system is in the deadlock. And suppose a finish of 0, finish of 1, finish of 2 is equal to false, then these are the three processes which are deadlocked. Okay, this is about the algorithm. If you have not got it, now I will take an example and explain the algorithm. Okay, let us take this example. Here we are considering 5 processes, P0 through P4, and 3 resource types A, B, C. That means the value of M is equal to 3. How many processes are there? There are 5 processes, so therefore N is equal to 5. Right? Now here I have written, and here we have also mentioned how many resources of each type are present in the system. There are 7 instances of resource type A, 2 instances of resource type B, and 6 instances of resource type C. So the algorithm, in the first step of the algorithm, what do? We simply assign available is equal to work. So what is available here? It is 0, 0, 0. So therefore this is assigned to work. And what do? See, we look at the allocation. If the allocation is not equal to 0, that is some allocation is made to these processes, that means there could be a chance that all these processes could participate in the deadlock. So we will make the finish of all these processes is equal to false. That is this process 0, 1, 2, 3 and 4. So we are going to make this elements of this array false. Okay, to start with. Now we have made work is equal to available, and we have made finish, all the elements of finish array is equal to false. Now in the second, this is the first step. In the second step, what we have to do? We have to see or look for a process whose request is less than or equal to work. Now you start from P0. What is P0's request? It is 0, 0, 0. So it is less than or equal to work 0 0 0. So therefore what can be done, you can make the the element that is corresponding to P naught true. So this can be made as true. Okay, and both the constraints are met. It was false earlier, and its request is less than or equal to work. So both these constraints are met. So therefore we make this true, and we also update the value of work. What happens to work now? The work will become 0 1 0. It was that was the allocation to P naught, so that gets added to work. So work becomes 0 1 0. After this, now again we proceed and see whether we can grant the request of P1. P1 requests 202, but we don't have so many resources, so that is not possible. Go to P2. P2 is its request is less than or equal to work. So therefore you make P2 true. Okay, this order you have to remember. First we could grant the request of resource P0, then P2. Okay, now what should happen to the value of work? Since I have all the elements of finish is false when I started with, so therefore I will not bother. So I'll simply update the value of work. So what should happen to the value of work? P2, this was the allocation made to P2, so we simply add this to work, so it becomes 3 1 and 3. Now with this can we meet the request of any other process? That we have to see. Let us go to P3. What is its request? It is 100. Obviously it is less than or equal to work, so therefore we will make this P3 is equal to true. Okay, then we put P3 here, and we let us modify the value of work. So what happens to the value of work? What has been allocated to P3 211, so it becomes 5, it becomes 2, it becomes 4. Okay, now we'll go to P4. P4 now this is its request 002, which is definitely less than work. So therefore now we can make this true, right? So P4 can be written here, and work is updated. So what happens to the value of work? Now this gets added to work, so work becomes 5 2 and 6. Okay, 5 2 and 6. Now let's go back in a round robin fashion and see whether we have any I whose finish is equal to false. P0, it has become now true, but there is P1 whose finish of 1 is false. And let's see what is its request now. Its request is 202. Can we meet with this whatever value we have in the work? Of course we can meet that. So because it is less than or equal to work, so therefore we now make P1 is equal to finish of 1 is equal to true, and we put P1 here at the end. And work becomes what? Work becomes what gets added? This gets added to the work, so it becomes 7 2 and 6. Now if you look at the number of instances of each resource type that are present in the system, so we finally arrive at this number, and with this order of execution of processes we could complete executing all processes. Therefore the system is not in a deadlock state, or it is not deadlocked. Okay, now we'll have to take an example, okay, where the system is in deadlock, and see how this algorithm is going to detect that. Let me go to the next slide. Okay, see here it is quite simple. What I have made now, made P2 to request an additional instance of C. So P2's what was its request earlier? Let us look at that. Okay, see here, P2's request was 000. Now we have made P2 to request another instance of C, or one instance of C, so it becomes 001. Okay, it becomes 001. Now what happens, let us see. Now if you start the algorithm, work becomes available. What is the value? That is, it is a vector which initially has 000, all zeros, so work is 000. Now with this available resources, can we meet the request of any of these processes? Yes, of course we can meet the request of process P0. So P0 can be executed. Now we will take whatever resources we had allocated to P0 and add it to work. So work is equal to, we have to see what was allocated to P0. Let us go back to the previous slide and see what was allocated to the P0. Okay, so what was allocated to the P0? 010. So 010 has to be added to work. We'll come back here. Now work becomes 010. Now let's check with this, can we meet the requirement of any of the processes? Can we meet the requirement of process P1 or request of process P1? No. P2? No, because it needs one instance of C, we don't have. And can we meet the requirement of P3? No, we cannot. P4? No, we cannot. So therefore, now what happens to the finish of P1, P2, P3 and P4? It all remains false. Okay, all remains false only. So in the fourth step, we check finish of these processes. Because the finish of P1, P2, P3, P4 false, we say that the system is in a deadlock state, and these are the processes which are contributing to the deadlock. Okay, this is how the deadlock detection algorithm works. Now that we have seen the deadlock different mechanisms for deadlock detection. First one is the wait for graph used for single instance of each resource type, and the second one is the deadlock detection algorithm, which is used for several instances of resource, when several instances of resource type is there in the system. Okay, now next we will discuss about after detecting the deadlock, how we can recover from the deadlock. Okay, let's discuss about different recovery mechanisms, how we can recover from the deadlock. The first approach, there are basically two approaches. The first approach is operating system need not bother. It will allow it to the operator, and operator, it will just inform the operator that the deadlock has occurred. Operator in the sense the user of the computer. And it is up to the operator to deal with it. So he can restart the computer or use some other means to overcome the, or kill the process to overcome the deadlock. The second approach is the system recovering from the deadlock automatically. So this is what we are interested in. In the next 2 or 3 slides, I am going to discuss about this approach. There are two approaches here. The first one is a process termination approach. The second one is resource preemption approach. So let us take up these approaches one by one and see what they are. Okay, the first approach is a process termination approach. Now let's assume that 4 processes are involved in deadlock. Okay, this can be found using the deadlock detection algorithm. So these are the 4 processes which are involved in deadlock. What the first approach says, abort all the deadlocked processes. You abort the execution of all these processes. But this solution is an expensive solution. Okay, this process P0 would have run for, let's say, 2 seconds, whereas this P3 would have run for 15 seconds and it is on the verge of its completion. So if you abort all these processes, then it is computationally very expensive, right? So this is the first approach. Or an alternative approach to this is abort one by one process at a time until the deadlock cycle is eliminated. So that is, you abort P naught. But the problem associated with this approach is that after you abort a process, you will have to run the deadlock detection algorithm, okay, to see the deadlock still exists or not. Abort the process P naught and run the deadlock detection algorithm. If the deadlock exists, then you abort the process P1 and so on. Okay, so what is the problem here? You will have to identify which process is going to be aborted first. How can we select a process to abort? That is using minimum cost, a parameter known as minimum cost. And this minimum cost depends on several other parameters. That is, what is the priority of the process? If the priority of the process is very high, then you cannot abort it. How long the process has computed and how much longer the process will compute before completing its designated task. This becomes very, very important. If a process would have computed for almost completion, then aborting that process would be an expensive one. And the next thing that you have to look for is how many and what type of resources the process has used. How many more resources the process needs in order to complete. So this is also very important. If the process just needs one more resource and it is available, then there's no point in aborting that process. Instead, you can select a different process for aborting. So here there are a lot of difficulties in this approach. That is, you have to select a process which is going to be aborted next to come out of the deadlock. So that's a difficult process, right? And after aborting every process, you have to run the deadlock detection algorithm to check the deadlock still exists or the deadlock is gone. Okay, so these are the two approaches which are used under the heading process termination. So this talks about terminating or aborting the process. There is one more approach that is called resource preemption, and let's see what resource preemption is. Okay, so what is the resource preemption? Here we take away the resources from some of the processes so that the deadlock can be broken, right? Okay, for that to happen, now from which process to take the resource from, that process becomes the victim. So the first challenge of this approach is selecting a victim. Again, some of the parameters that we discussed in the previous slide for selecting a process to abort, some of those parameters could be used here for selecting the victim. That is, if the process has run for a longer time, then such a process should not be selected as a victim. Okay, so this is a challenge in case of resource preemption. The next challenge in case of resource preemption is, let us assume that you have selected a process as a victim and you are going to take away the resource allocated to that process. But you cannot leave the state of the process there. You will have to roll back its state to its previous safe state. So that's very difficult. So you will have to maintain at every regular interval of time, you will have to maintain the state of all the running processes, which is expensive, computationally expensive. So here what people normally do is they instead of rolling it back, they abort the process. Okay, so that's the approach they use. Another challenge associated with the resource preemption is starvation. That is, you should not select the same process P again and again for taking away its resources, allocated resources, or for aborting this process. If that is done, then this process is going to starve. So that's a challenge. So you have to avoid starvation. How to do that? You can put a maximum limit on number of times this process could be aborted. So that can be a solution, right? So what is resource preemption? We select a process and take away all the resources from that process and run the deadlock detection algorithm to see whether the deadlock still exists. If the deadlock exists, then we select one more process and take away all its allocated resources. We go on doing that until we find that there is no deadlock in the system. So this approach is called resource preemption approach. So with this, we have finished discussing about the deadlocks. We have discussed about the necessary conditions for deadlock to occur, and we have discussed about three different approaches to handle the deadlocks. The first one is the deadlock prevention mechanism. The second one is the deadlock avoidance approach, and the third one is the deadlock detection and recovering from the deadlock. Okay, so with this we have completed our discussion on deadlocks. Let me go to the next topic, that is memory management. Very interesting and very important, memory management in operating systems. Okay, let's move on to another interesting topic, that is memory management. Now, before I discuss about several memory management mechanisms used in the operating system, let us recall whatever we had discussed about memory in the introduction to operating system module. Well, let me go to this slide. Recall that we have hard disk and main memory and cache memory and registers. Now, as we go from CPU towards hard disk, the memory capacity would increase. That is, the storage capacity of the hard disk is obviously more than the storage capacity of the main memory, and similarly the storage capacity of cache is less compared to the storage capacity of the main memory. But whereas if you come from hard disk towards CPU registers, the speed of accessing the data or instructions would drastically increase. That is, if you are accessing the data from hard disk, it is data or instruction from the hard disk, it is slower compared to accessing it from main memory. Okay, and what is stored in the cache? The frequently accessed instructions or data of a process is stored in the cache. And we also know that the program, when we create the program and the associated data is stored in the hard disk. After the program is compiled and when it becomes loadable, then it is brought into the main memory by the loader, and the CPU will fetch instruction by instruction from the main memory with the help of a register called processor register called program counter or instruction pointer. So this will always point to the instruction that has to be next fetched into the CPU for execution. Every time an instruction is fetched into the CPU and executed, the content of program counter is updated so that it points to the next instruction. This is what we have already discussed. And the main memory is divided into several memory locations, and each memory location is capable of holding a byte of data, and every memory location is identified by an address. and the size of the address depends on the width of address bus, and the storage capacity of the main memory also depends on the width of the address bus. For example, if the address bus has 16 lines, or if it is 16-bit address bus, then the storage capacity of the memory would be 2 to the power of 16, right? So this is what we have discussed. Now let's see and let's look at the organization of the main memory. In this chapter, or in this module, we'll be basically concentrating on management of main memory, right? So the cache memory management is altogether a different topic. We will not be discussing about the cache memory management. We will be discussing about only main memory management in this chapter. Okay, if you look at the memory, it looks like this. A part of main memory is permanently given to operating system programs, and the remaining part of the memory is given to user processes. That's what you are seeing here, and the data associated with these processes are also stored in the main memory. Now let's see what is the hardware support that operating system gets to manage the memory. And we know that once the user processes and operating systems are loaded into the memory, now this becomes the address space of operating system, and this becomes the address space of this process. If it is process P1, this is going to be the address space of process P1. And you know that when process P1 is executing, it is not supposed to touch the address space of other processes. For example, it is not supposed to touch the address space of P2, or it is not supposed to touch the address space of operating system. So this is what is known as memory protection. We had a very little introduction to this memory protection. Now here let's see how operating system ensures this memory protection. Okay, I'm repeating, memory protection is nothing but not allowing the processes to access the address space of other processes, and not allowing the user processes to touch the address space of operating system. That's what is memory protection. So what is the basic hardware support that operating system gets for this memory protection? That's what I have shown in this diagram. Let me clear this. Yeah, you see here 2 additional registers are provided. They are base register and limit register. Okay, once the process starts its execution, let's say this process has started its execution, operating system loads some values to the base register and the limit register in the kernel mode. Okay. Only the operating system can load the values to base register and the limit register. So what is the value loaded to the base register? It is nothing but the starting address of the process, that is this. Okay. This is the address stored in the base register, and what is stored in the limit? That is offset from the starting address. I will explain this. For example, let's say the starting address of the process is 300, and this is what is stored in the base register, and the program is going to utilize 40 locations. Then this becomes the offset. So this is what is stored in the limit register, and the value which is stored in the limit register could be used to calculate the ending address of the process. The ending address of the process is nothing but whatever is there in the limit register and whatever is there in the base register. Okay, so both are added, you get the ending address. So starting address of the process is 300 and the ending address of the process is 340, and this becomes the address space of that particular process. Now how we can ensure that this process, every time this process generates some address, that address lies within this range. So that is what I have shown in this diagram. Let's say CPU is generating some address. This address is compared with the content of base register. So this address has to be greater than or equal to the content of base register. If yes, then it is the address is checked with the base plus the content of base plus limit content of limit register. So that is this end address. So the address has to lie within this range. If yes, then that address is used to reference the memory location. That means that is it is the address which falls within the address space of the process which has generated this address. Okay. Otherwise, a trap is generated to the operating system, and the operating system will display an error, and it will stop further processing, further execution of this process. Okay. Till now what we have understood about the addresses, these addresses are nothing but the physical addresses of the memory locations. But let's see, there are different addresses that are generated during the process of during the life cycle of a process. Let's see what are those addresses in the next slide. Okay, the address binding happens at different times. It could happen, it happens at the compile time, load time, and the execution time. Let's try to understand what is this. If you have written some assembly code, then we represent address something like this. Let's say add 1. We also call it as a label and write some instructions here. Instruction here, move AX comma BX, something like this. Then we say jump to add 1. Okay, so this add 1 is representing the address of this instruction. So what we are saying, that after executing all the instructions which are present here, you jump to this add 1, which is the address of this instruction. So this kind of address is called a symbolic address. Okay, this is called a symbolic address. So at the compile time, whatever you find in the source code are all the symbolic addresses. So what happens at the compile time, these symbolic addresses are converted into relocatable addresses. Remember this, relocatable addresses. What is relocatable addresses? I will tell you. Now, for example, if this program starts at an address, let's say 3000, and this add 1, this instruction is at an offset of 400 from the beginning. Okay, so relocatable address is this. No, actually what is given to add 1 is 400. What we say that this instruction is at an offset of 400. This is a relocatable address. Why? Because see, when this program is loaded into the memory, it may get loaded to a memory location which may start from 3000, or it may get loaded to memory whose starting address could be 4000. So when it becomes 4000, the relocatable address would still remain the same. So it is at an offset of 400 from the beginning. So relocation becomes easy. So that's why these are called as relocatable address. So that's what is the address that gets generated at the compilation time. And what happens at the load time? Now you have relocatable addresses, and these relocatable addresses are bind to the physical addresses of the memory location. For example, you had that relocatable address 400, and the program is loaded to memory starting from 7000. So this gets converted into relocatable address, gets converted into 7400. So that's what happens at the load time. And at the execution time, what happens? See, you have CPU generating the addresses. Now what CPU generates is not the physical address of the memory location. It generates what is known as logical address or virtual address. For example, actual address of the memory location or the physical address of the memory location is, let us say, 7349. So what CPU generates is this 349. That's nothing but the logical address. So you have to understand what happens at the execution time. At the execution time, the address generated by the program is called the logical address, and this logical address has to be actually mapped to physical address. Physical address is the absolute address. Logical address is also called as virtual address. So set of such logical addresses generated by the CPU is called logical address space. Okay, logical address space. And similarly, the set of physical addresses of a process constitutes a physical address space. Now, one thing that came up during our discussion is that this logical address has to be mapped to physical address, and this mapping is done by memory management unit. That is also a software, that is also hardware which supports memory management. In the next slides, let's see the organization of the memory management unit. Okay, let's see here. We have memory management unit which has got a relocation register. So this relocation register is loaded with some value by the operating system in the kernel mode. This is something like the base register that we discussed in one of the previous slides. Now the CPU generates a logical address, that is in this case logical address generated is 346. A memory management unit has to map this to the physical address, that is this 1414346. Okay, so what is stored in the relocation register? It is 14000. That is like the base address of the memory segment in which this process is residing. That is added to the logical address generated by the process and to generate physical address. So this is how the logical address is mapped to the physical address in the memory. So this we will have to keep in mind. We will elaborate on this when we discuss about different memory management scheme. This is very important. The addresses generated by the CPU or the program when it is getting executed, those addresses are logical addresses, and these logical addresses are to be mapped to physical addresses, and this is done by memory management unit. Okay, now that we have understood that the program, if we have to execute the program, it has to be brought from the hard disk to the main memory. Okay, so let's say we at the load time we bring the entire program P into the main memory. If that is the case, then what happens is the program size cannot go beyond the size of the main memory. So that becomes a limitation. Now, how to overcome this problem? This problem could be overcome by using what is known as dynamic loading. So this dynamic loading is postponing the loading of any code or any routine procedure till it is required. That means when the CPU makes a reference for some instruction, if that instruction is not present in the main memory, only then it is loaded to the main memory by the operating system from the hard disk. So this is known as dynamic loading. That is, the entire program is not loaded into the main memory. Only the main program or the main procedure is loaded into the main memory, and as and when required, the remaining part of the program is loaded into main memory. This is called as dynamic loading. A static loading is what? Loading the entire executable version of the program into the main memory. If we do that, then only the program which is having size less than the size of the main memory can be brought into main memory. So with this dynamic loading mechanism, we are dividing the program into the parts, and we are only bringing the part of the program into the main memory, and only when required the remaining parts are brought into the main memory. This is called as dynamic loading. Now let's see what is dynamic linking of libraries. Okay, so you know what is linking. That is, once the source code is compiled, okay, by the compiler, you get the object code, right? The output of the compiler is the object code. Let's say OC object code. So this object code is the input to the linker loader. Let's say we combine the operation of linking and loading into one module, and we will call this as linker and loader. So what this linker loader does, it links the object code of libraries which are required to run this program with the object code of this program, and produces loadable image which is loaded into the main memory. Or you can also call this as exe, loadable image, or .exe, which is loaded into the main memory. Okay, so this linking is called static linking. That is, at the time of linking, the object code of the source file with the object code of the libraries. So that is happening at the linking time. So what is dynamic linking? Though this linking operation is postponed till the execution time. Okay, so that is only when the program is running. If it needs some library to be executed, to be called, only at that time that is linked to the program. This is what is known as dynamic linking. I hope the dynamic loading and dynamic linking of libraries is clear. Okay, let me quickly tell you once again the difference between the dynamic loading and the dynamic linking. In dynamic loading, the whole program is not loaded into the main memory, but only the main part of the program is loaded into the main memory, and as and when required, the remaining parts of the program is brought into main memory. That's what is known as dynamic loading. Bringing the entire program into the main memory at once is known as static loading. And what is dynamic loading? The linking of object codes of libraries will not happen conventionally. This process is postponed to the execution time. So only during the linking and loading time, only what is known as stub. I don't want to elaborate here. If you are interested, you can study more about this dynamic linking. What is known as stub is included with the object code of the source program during the linking. This stub is a small piece of code which will have the information about where the required library is residing in the memory. So when that library is called during the execution time, the stub will help the operating system to locate that library and then load it to the main memory from the hard disk. So this is what is known as dynamic linking. So let me stop here. I think we are running out of time. I'll discuss about different concepts associated with memory management in the next class. Thank you.